All right, so in this video, we are going to continue the little series here on flow control, and we are going to look at while loops. So up to this point, we primarily, when we've been looking at loops, we've been looking at for loops. And for loops are, of course, very useful when you have a fixed set of items and you want to perform some computation for each element, right? So you would, a for loop, so for item in whatever that collection is or that container is. So we've seen things like, for item in a list or a dictionary. But the key thing is we've got some type of container that has various items, and we want to perform computations for each element in that container. In contrast, while loops are going to be used when we want to continue a series of computations as long as a particular condition is satisfied. So we don't know exactly how many iterations of this loop will execute, but we're going to use some type of condition to help us understand when to terminate the loop. All right, so we're going to start off by just looking at kind of a basic format of a while loop, and then we will do another example that is kind of more aligned with the area of optimization, which is an area where I tend to do a lot of work in, and as a result, I end up using while loops a lot in that context. All right, so let's just look at the structure. So first thing, to kind of set things up, I am going to create a variable called threshold, and I'm going to set that equal to 1 million. And what we're going to do is we're going to use a while loop to come up with a dictionary that contains all the integers starting at 0, and the value if we were to raise 2 to the power of that integer. And we're going to do that for all integers where that exponential term is less than or equal to 1 million, right? So we're going to try to find a set of small exponential numbers, where by small, I'm saying I'm considering anything less than 1 million to be small. All right, so I have got a variable threshold here. Notice that I'm using all caps when I define that. So that's a very common variable naming convention when we are trying to define a constant in a program. So this is what I'm indicating here by setting all caps, is saying, hey, this is going to be a constant value that's going to be used in our program, and I don't intend that value to change through execution of the program. All right, so that's all I'm doing to indicate. So I've got this capital threshold. That's going to be essentially the cutoff. We're going to keep iterating through integers as long as if we raise 2 to the power of that integer, that resulting value is less than this threshold, or 1 million. And I've got an empty dictionary, I'm going to use an empty dictionary to kind of keep track of things. All right, so that's just kind of the setup. So we've got this empty container, and then I've got this threshold, which is going to be part of my condition. And what I'm going to do, remember I said I wanted to have, essentially looking at the integers, or, the positive integers in 0. So I'm going to create this variable in and set that equal to 0. And I am going to create or compute. Let me go ahead and do this. Thinking and talking is not working out. Or thinking and typing, as you can see. All right, so I'm going to compute that exponential value. So for each integer that we encounter here, right, we're going to compute this exponential. So we're going to take 2 and we're going to raise it to the power of whatever n is, or our current integer value. All right, and here is going to be our while loop. All right, so I'm going to say while. Notice as soon as I type while, we get that green bold text, so that is a reserved word. And I'm going to say while the exponential value is less than or equal to my threshold. So that was all caps. Okay, so while that is true, while this expression is evaluating to true, we're going to continue in this loop. All right. And what we're going to do is anytime that's true, I'm going to save in small exponential numbers. So I'm going to create a new entry in that dictionary for the current value of n, and I'm going to save the exponential value that is computed, and then I'm going to update n and recompute that exponential value. All right, so let me do that real quick. So if you wanted to update n, we're just wanting to increment this by 1. So you could do that like this. You could say, well, overwrite the value of n to be n plus 1. Or another way that you can do this is a little bit more concise, is you can do n plus equals 1. All right, so those two things are going to just both increment the value of n by 1. And then I am going to recompute my exponential value. All right, so I'm going to run this real quick, and then we will go back through and we will talk through this and make sure that everything is understood. All right, so it runs. That executes pretty quickly. And now if I were to print out my small exponential numbers, we can see that the integers that we are stored in that dictionary. So we started at 0 and we're incrementing by 1, and the integers are 0 through 19. And let's just do a quick check, and let's say, well, if we had taken 2 and raised that to the power of 20, right, we would have got 1,048,576, which exceeds our threshold. So when we cut off at 19, we in fact did cut off at the integer where that resulting exponential value is less than or equal to 1 million. All right, so let's go back and let's look at this loop. Let's just make sure that everything's understood, what we're doing here. And then we'll look at a couple of caveats. All right, so again, we've got our threshold, we've got our empty container, and then we initialized the thing that we're going to essentially be incrementing over. And so this is very kind of common when we're dealing with while loops. There's usually going to be some type of initialization type of code. So if you recall with a for loop, we have a list, and I'm going to say for item in this list, do something. Right, so we don't really need initialization. You might want to have another container, an empty container that you store the results of computations in, but there's really no initialization needed. But in a while loop, that it's very common that you will need to do some initialization, right? So in this case, right, our condition is based off of this exponential value. All right, so I've got to come up with, an initial value for that. So when it hits this loop, that it actually has a condition to check, right? So I initialize, I say, well, my value of n is 0. My exponential value is 2 to the power of n. So when it hits this while structure, we have that first exponential value to compute. All right, and the way that I've set up this loop is purposeful. So we're always doing the computation. So I initialize with the first computation and immediately store it. All right, and then once it's stored, that's when we do the increment, and then we move back through that while structure, only adding values if they have met that threshold. All right, so pretty straightforward. All right, let me restart the kernel. One thing that I do want to mention, and this is, a lot of times when if you've done any programming in other languages, or you go out and read things on the internet about while loops, people will always have the caveat of you've got to be very careful, right? Because with a for loop, we've got something that we're iterating over. So it's for a particular sequence, right? So if you've got a list of 1,000 items and you say for item in list, well, that loop is at most going to execute 1,000 times. Right, because you're doing it for each one of those. So you can kind of bound how long that thing is going to run, right? So it's going to have essentially a deterministic almost runtime. All right, with a while loop, you've got to be very careful, right? And in particular, you've got to make sure that whatever condition you've put on that while loop structure, that you have appropriate code down below that is actually going to result in cases where that condition becomes false. Right? Because otherwise it will just run forever, and that's oftentimes referred to as an infinite loop. All right, so let's look at a couple of cases just to make sure, and then I'll show you how to get out of that in Python. So you don't, maybe you don't want to run this because I'm about to, create an infinite loop, but it's going to be, pretty harmless in this context, and with the notebook we can get out of it pretty quickly. All right, so let's think about this. So in our loop, we initialize n, we compute that exponential, and then we check to see if that exponential value is less than that threshold, and we store it. Then we need to go check the next value of n. Well, what if we had forgotten that? All right, so what if we had forgotten to increment n? All right, so n is originally equal to 0 in this line. We compute the exponential. Okay, if it passes this, which when n is equal to 0, this is going to be true. So we're going to enter our while loop, and we will save essentially that key in value in our small exponential numbers. All right, but if we forget to increment n, when we go down here to this line and recompute that exponential value, n is still going to be 0. Right, so it's going to go through. Now it checks at the while structure, and it says, hey, this is still a true statement, so add that and continue on. And if we never increment the value of n, then we are going to continue to run. So how will we notice this? Well, I'm going to hit Shift Enter. notice right here we've got an asterisk. So when a cell executes, it's going to give us a number that's indicating, okay, well, the position or essentially the sequence of which that cell was executed in. So a 1, 2, a 3. But it's still running. So when you see the asterisk, that's telling you that the cell is still computing. So in this case, the loop is just running. All right. Now, wood is checked, so I could select this cell and I could hit stop. All right. So that'll be a keyboard interrupt. So that just stops that cell. And if I look at small exponential numbers, I've only got one entry. So it was running for all that time and it just computed one thing. Well, what was that? It was, well, n, we never incremented n. So it was just recomputing n is equal to 0 over and over and over again. Right. So you've got to make sure that you have, the appropriate logic underneath for that loop to actually execute. Now, of course, if I were to put in, put that statement back in there, make sure we increment in, it executes really, really quick. And one thing I do want you to realize is, just the fact that your cell takes a little bit of time to run is not an indicator that it is an infinite loop, especially if you're doing really computationally intensive things for each one of those values. So it can take some time to compute, but you should have a good sense. I would maybe test out my code with a couple of values, see how long that computation time is, and then you can kind of see, or you can even use, some other means. I would avoid using a print statement. If you're saying, okay, well, I want to, see as n actually incrementing what's going on in the loop, people might be kind of tempted to put a print statement in there. Just to kind of, see what's going on. But the problem is if you do a print statement, these loops are going to run really fast. Like if I were to put a print statement to try to debug this loop, it's going to print, maybe we're printing the value of n. Well, it's going to print that to the screen a lot of times very quickly. And since in this case, we're using Jupyter Lab, it could actually print it to the screen so quickly that all of the text that it's printing causes a memory issue on your computer. So that's kind of one of the things. You could essentially run yourself out of memory with print statements. Just to show you that, let's see, I'm going to use a little bit of logic. I'm going to put an iteration counter. And I'm going to take this out. Let's say, okay, well, I don't have my value of n incrementing correctly. So maybe I don't know what's going on. Of course, we obviously know what's going on in this very simple while loop. But let's say that we didn't. And we were going to, print the value of n to do that. I'm going to put this iteration counter down here at the bottom, make sure that that's nested under. And I'll do a plus equal 1. And then I'm going to say if iteration is greater than 100, let's break. So using some of the other concepts that we've seen in flow control, basically all I'm doing here is I'm going to show you how fast it will print these values to the screen. But I'm making sure that, okay, well, after we've done 100 of those, break it. Right, just so I don't run my own machine out of memory. Right, so it prints really quick. Right, so you can imagine if you didn't have, if you said, oh, I'm just going to debug this program using a print statement, you're going to print a lot of characters out to your screen, and Jupyter Lab's running in a browser, so it might cause you some memory issues. Again, that's just demonstration. So our while loop, just to go back to what we had, we've got n plus 1, and that. We can take this out and that should run. And I'm just going to pull the output right into that cell. All right. So that is a basic example of a while loop. All right, so we're going to do one more example, and this is going to be kind of motivated from, the area of mathematical optimization. So let's say that we had some type of a function, right, that describes some process, or we can put in arguments and it does some type of computation, and it translates the arguments that we put into a value that maps some process. And we want to figure out the input that makes that function value as large as possible. In particular, the function that we are going to look at is, let's call this function y, and it's going to be equal to negative x squared plus 4x plus 5. All right, so let's say that we've got, some process where we've got an argument x, and depending on that argument x, whatever that takes on, this expression is going to give us a value, and we want to make that value as large as possible. All right, so again, this is just very generic. And so what we want to do is we want to find a value of x that maximizes y, makes y as large as possible. Now, one thing that I'm going to kind of gloss over here, so we're not going to, we haven't looked at plotting, and that's not the focus of this video, but you can think about it. So this is essentially going to be, a parabola, an inverted parabola here. And then we've got some additional terms that are some using x and some are just constants. But it turns out that this function does have a unique maximizing point. Okay, and you can actually find the point that maximizes, or the value of x that maximizes it by taking the derivative of this function and setting it equal to 0. And you can actually, again, take the second derivative and use the second derivative test to actually make sure that that point is a unique maximizer. But we're not going to go through that. What we're going to do is we're going to kind of brute force this. So we could solve this with calculus, long story short. But we're going to use a while loop to solve this. Okay, and the way that we're going to do this is we're going to pick a value for x. So we're going to pick a starting point, a really, really small value. And then what we're going to do is we're just going to increase that value for x from that starting point at a certain step. So we're going to say, okay, well, we've got a starting point that we know, is, maybe not, it's far to the left of that maximizing value, or it's below that maximizing value. And then we're just going to slightly increase it over time, keeping track of the value of y for each step in that x. And then as soon as we find a point where, as long as we're getting improving or increasing values for y, we're going to continue doing this process. And then as soon as that turns out not to be the case, so as soon as we get a consecutive value that is lower than the previous value, we're going to terminate the loop. All right, so it's essentially going to be a search procedure. So this would be like implementing a search procedure in an optimization kind of context. And again, the nice thing here is, we can use calculus to verify that this function actually has a unique maximizer. So if we didn't have that, guarantee, we would have to do something else. But in this case, we can do this kind of search procedure based on a step. All right, so let's code this up. All right, so I'm going to do, first off, I'm going to make a parameter, or a constant, I should say. Our step size, let's just set that equal to 1 for now. 1.0, I'll do that as a float. And let's say that our initial value for x is going to be -20. All right, and we will come up with an expression to compute our y value for that particular value of x. And actually, we can just copy that expression down. All right, so we run this. All right, so when x is 20, y takes on a value of -475. All right, now what we want to do is we want to continually increase x by our step size until we reach a point where this y value starts to decrease. So what we would expect is as x increases, that y is going to be going up. And then we're going to hit a point where when we take one additional step, that value actually goes down, and that's where we want to terminate our while loop. All right, so this is going to be a very common type of structure. And what I'm actually going to do, instead of actually having the conditional, I'm just going to use a flag. All right, so I'm going to say improving. And I like to do these in all caps as well, just to kind of indicate that this is a flag variable. I know the value of this variable is going to change over the iteration of my loop, but to me, this is just a personal preference. I like to set my flag variables as all caps, just so they kind of stand out to me in the code. All right, so initially I'm going to set this improving is equal to true. All right, and my loop is going to say while improving. Okay, now remember, this is going to be true. Okay, so it's going to say while true. So it's immediately going to go in there for that first execution. All right, so this is my initialization code. So I've got x, I've got an initial value of y, and then I have set a condition, right? And using this stuff that I've defined, I've made sure that I can enter the loop, right? So if I were to set this is equal to false, and then right here just print let's just print in loop, right? It doesn't even go into the loop, right? So the thing is, you've got to have a condition that evaluates to true initially, right? So whatever initialization code is necessary for that to be true, you need to make sure that that occurs. All right, so what I'm going to do is now I'm going to set improving equal to true. And the first thing that I'm going to do is toggle improving equal to false. So this is just me kind of safeguarding. I want to make sure that I can get into the loop, but immediately when I'm in that loop, I'm going to do something to make sure that it's false. So in this case, previously we were using this computed numbers, and we had to make sure that our n was growing accordingly and to set that condition. And to avoid an infinite loop here, one thing that I'm going to do when I'm using this kind of structure is I'll have this flagging variable, set it to true, enter the loop, and immediately set that thing to false. That way, I've got to use computations below to actually drive that variable being set back to true. All right, so what we'll do is I'm going to say, okay, well, if that's true, so initially I'm just going to say improving is true, and then I'm going to take x, and I'm going to add to it whatever the value is stored in my step size. All right, so it says improving, which means I'm getting larger values for y. So we get in there, so I increment x, and then I recompute y. All right, now one thing that we need to do, I actually need to add just a little bit to my initialization code. What I need to do is I need to store a best x, and I'm going to make that initially equal to x, and then I'm going to say max y, and that's initially going to be equal to y. So now in my initialization code, not only did I compute x and y, but I've created these two variables to keep track of which x gave me the maximum value of y and what that maximum value of y was. All right, so we're in our loop. It was still improving, so we continued. So we updated x, and we're going to recompute y. And what we'll say is if this value of y that we've just computed is greater than max y, so it's greater than the maximum y we've seen up to this point, what do we want to do? Well, I'm going to update best x and max y, being careful of my indentation under that if statement. I want these two things to be executed only in that situation. All right, so if this condition is true, so the value of y is larger, well, we found a new x that gave us a larger y, so we're going to update best x and max y, and I'm also going to set improving equal to true. Right, so basically what I'm essentially flagging here is that, okay, well, we found when we increased x by this step size, the value of y that returned from that was better than any we'd ever seen, where better is defined as larger. So we updated our best and max y, best x and max y, and we said, yep, we're continuing to improve. All right, and at the very end of this, I'm just going to print some statements. Let's do f, let's just print out best x, what that equals, and let's print out max y. All right, so we can run that just to kind of test, and we can see the best x it found was 2.0, and that gave us a maximum y value of 9.0. All right, so we can change our step size if we wanted to make a more fine-grained search. So if you think about it, let's just look at how many loops this goes through, or how many executions of that while loop. So if I were to keep track of my iterations, I'll set that equal to 1. And then every time we get an increase, I'll do iterations plus equals 1. All right, so that went through 23 iterations. Nice, so going from -20 all the way up to 2. If we were to change the step size, that can allow us to do a little bit more fine-grained search. So 0.1. All right, so it still finds a best x of 2, but it took a lot more iterations, right? And again, just depending on what that function is going to, it might not be that, of course, that our best x value would be an integer number. Now, I do just want to make a quick little comment. This is not the purpose of this video, but notice this. This is quite interesting, right? So the best x is 2 dot many zeros 16, right? So you might say, well, gosh, how did it get there, right? So we started off with x equal negative 20, and we're adding steps of 0.1. So we're never doing something out in that, these far decimal places. So why are we getting a many zeros and then a 1/6? How does that happen? And it happens because of floating point arithmetic. And this is not a Python thing. This is a programming language thing and how your computers represent numbers. So if you imagine with a floating point, there's essentially an infinite number of decimal points. So whenever it's doing computations, right, there can end up being some numerical inefficiency or inaccuracy in those far decimal points, because you think about it, since there's an infinite number of possible decimal points, you don't want that actually to be stored on your computer, right? Because storing each one of those characters for those decimal points, that's taking up memory on your machine. So technically a floating point, all of your floating point computations in a computer are to a degree rounded, right? You can set different precisions. Different programming languages might have different capabilities with respect to precision, but this is why you end up seeing some type of representation like this, because in this case we're continually, we're incrementing this float value over 221 iterations. So you're getting some inaccuracies, largely some rounding errors in those floating point representations, and that will lead to something like this. So you do have to be careful, because if I were to say now best x, let's see this, is it equal to 2? That's false, but that is 2 essentially, right? It was some floating point inaccuracies. That's one thing that you definitely need to be careful about with strict checks, in particular if you are working with floating point values. All right, so one thing, and later on, we might see there might be some other videos with libraries that can help you do this. Check and see, instead of does it equal something, is it close to something? You could come up with your own checks that do something very, very similar, or you could even, convert this, just do a round if you're trying to do some type of comparison to make sure it goes. But again, you just ultimately have to be very careful. All right, so that is going to do it for while loops, and that is actually going to do it for the little mini series here, I guess, on flow control. So with that, we will be done with flow control, and then in the next video, we're going to start looking at comprehensions in Python.